So, hello everyone. What if I told you that the same mathematical principles that help your brain recognize faces can be coded in just 20 lines of Python? I am your favorite community contributor, Hasanul Banna Himel. Today we will be learning about the neural network fundamentals. By the end of this video, you will code your first neural network that can solve logic problems. Now, what you can do is you can comment below what's one thing you hope to understand about neural network by the end of this series. So, here you can see we have a human. Here you can see we have a simple neuron. Here we have cell body, we have dendrites, axon, synapse. What we know that dendrites receives the information, then passes it to the cell body. It processes the information, and axon transmits the information. So, what is our key concept from here? What we learn from here is neurons fire or don't fire based on input strength. Now, here you can see we have a computer neuron. Here you can see we have some input values. Then we have our x1, x2, x till xm as our input values. And here we have some of our weights, and after adding some biases and after using the activation function, we get some output. So here what we're doing is we're mimicking the decision making process, not the biology. So what you can do here is you can pause here and try to draw your own version of both neurons. Okay, so now comes our most amazing part, or my personal favorite one, the mathematical problems. So let me just delete. Yeah, what are we going to call this is we are going to call this our, let's say, we are going to call this our mathematical foundation, as it will be helping us to learn the details. So we are going to cover some concepts here, like we are going to divide this into like 8 stages. Like in the stage 1, what are we going to see is we will be using the simplest case. Then we will be let me just make this a little bit smaller. Yeah, maybe a little bit. Yeah, I think this should work. Okay, so this will be stage 1 will be our simplest case, and for step 2 it will be have our multiple inputs, and on the stage 3 what are we going to do is we're calling this like the adding bias. As I am separating this part by part, thus it will be helpful for you to learn or understand the topics properly. Okay, then we're going to call our stage 4 is it will be calling our activation functions. Activation functions. Then we will be going to have our I think this would be enough, like just a few more concepts maybe. Nah, on my opinion, like this will be enough. Yeah, by 4 this will be needed for our today's video, so we will be covering just these concepts today. Okay, so here we will be covering the simplest or the single neuron one, the multiple inputs, and then how the bias works and the activation functions. So if we move on, so at the first, how does this actually these things work? Like here, like if I write the simplest, okay, the simplest list. Okay, so if you here, what are we going to learn is we will be having a single input and a single weight. So what are we going to use here is we will be using a single input and weight to understand this concept. And if we write the thing here, yeah, so let's say as a single input we add some single weight, and it's here we have some values, and then our output here. Okay, so here what are we going to do is we're starting with our output x1 and w1, or our input 1 or the weight 1. If x1 is, let's say our x1 is 3 and our w1 let's say it is 0.5, what will be our output? Our output will be 1.5, right? So the weight controls how much the input matters. Like we can do, like, let's make the our input constant, and if we tweak our weight a bit, let's say our weight is, let's just change the whole thing, maybe that will be better. Yeah, so okay, so let's say our input is 2 and I have a weight, let's say 0.3. What will be my output here? If I multiply these both, I will be having an output of 0.6. Again, if I have an input of 2 and I have, let's say, a weight of 0.8, I will be having another output of, let's say, 1.6. Again, if I multiply our this, like if I have a negative amount of weight, let's say negative 0.5, what are we going to have the output? Our output will be -1. So weights are like volume knobs. They amplify or reduce signals. So this was our simplest one. Now we move on to our multiple inputs. Let's say we have our multiple inputs. So let's say again we have our x1, our w1, our x2, our w2, our x3, and our w3. If we do the math, simple math here, what are we going to do is we are going to summation all of this, and thus we will be having our output. So our output is, like, if I write this into our equation, it will be something like this. Our output is x1 w1 plus x2 w2 plus x3 w3. Now the output is like the summation again. If I write this in x1 multiplied w1, so this will be our output, this in our what is this called, the summation notation. So like, what are the different scenarios we can like do? Like, if I have a positive weight, let's say I have some weights here. If I have a positive weight, it will vote for the input. It will vote for the input. If I have a negative weight, it will vote against the input. And if I have a zero weight, it won't have any influence at all. Now, our third part, or the adding bias. So, if you look at it, it is more likely the constant terms, like what happens when all inputs are zero. Like with the current equation, let's say I say equation here, output say 0 multiplied w1 plus 0 multiplied w2 plus 0 multiplied w3 is equal 0, right? So the neuron is always off, or no flexibility. So what are we going to use here is, we will be using adding some biases, or like, more likely the equation will be something like, let's say x1 w1 plus x, what am I writing here, yeah, x2 w2 plus x3 w3 plus some bias to like have us, it will give us some output, like if, what if we have any corner case here, so we won't be facing these types of issues. Now our final one, the activation function. Activation function. So here, from raw scores to meaningful outputs, like let's say we have a problem, like our z can be any values, like from negative 1000 till it will can be from 0 to positive 1000, it can be anything, right? So we need bounded interpretable outputs. Like we have some functions, like if I just name it out, we have discussed these things earlier, like the step functions, then we have our the sigmoid function, then we have our, what is that called, the ReLU function, so they have different like equations of them to, like let's say for the step function, it is something like f of z, as I still remember, if 1, it will be 1 if our z is greater than or equal 0, and it will be 0 if our z is less than 0. Yeah, that was our step function. And the sigmoid function is more likely like the sigmoid of z. Here it is 1 over 1 multiplied, or addition exponential power negative z. Yeah, this was it. Yeah, so here, and finally for the ReLU, we know that like the z, it will be z if our z is greater than 0, and it will be 0 if it is the z is less than or equal to 0. Yeah, so correct me if I am wrong, as I maybe forgot some concepts later on. So now we learned about the activation functions. Now comes our next part, or how actually a neural network works. A neural, more likely a neural network structure. Okay, so if we have a neural network structure, let's say I have let's say I have a single neuron here. This is my, let's say this is my x1. Then we have some hidden layer. Let's say this is my hidden layer. This is my, let's say, hidden layer, and this is my output. And then again, if we add another input here, let's say this is our x2, and again this one, and let's say yeah, and this one too, this one, and then this one, it will be our output. So what are we going to see is now the feed word, or the feed forward structure. So here we have the, if we look at the feed forward, it has some key principles, like it does like information flows just in one direction, like from input till the let's say from input in the hidden layer and in the output. And each neuron in layers connected to all neurons in the next layer. And one of the key principles of feed forward structure is no cycles or no backwards connections yet. So if we, like, let's say if we look at the key definitions for the feed forward network is where the information flows in one direction. We have a hidden layer, like the intermediate layer that processes features, and layer, it is a collection of neurons that process inputs simultaneously. Okay, so now we are going to cover the forward propagation. The forward propagation. Okay, so let's say I have three inputs. I have two hidden layers, and I have one output. So if I connect this with all of this, let's do that first. Yeah, and then I have output here. Okay, so like let's say I have some real inputs, like let's say this is 1, this is 0, and this is 1. From input to hidden, like let's say for z1, the equation will be something like w11 of our this input 1 plus w12 of our second input 0, and w13 of our third input 1, plus our additional bias 1. And again we will be having our activation function here, like thus we are going to using the sigmoid of z1, just this, like, yeah. So okay, now again for the z2, z2, here we will be having our z, my bad, w21 of 1 plus w22 of 0 plus w23 of 1 and our bias 2, and for the activation, second activation function, the sigmoid of z2. Okay, so this is our input for like from here to here, from input to hidden function. And for hidden to output, this was for our input to hidden, and now we're going to write the hidden till our output. So for this we have another one, z3 of w31 of our a1, our activation 1, plus w32 of our activation 2, and in addition our bias 3, and final activation here, the sigmoid of z3. So the key insights here are that each layer's output becomes the next layer's input, and it's just a matrix multiplication and activation functions. Now if you want some key definitions, like the forward propagation is more like the process of computing outputs from input through the network, and what is the matrix multiplication is efficient way to compute all neuron outputs simultaneously. Now we are going to see our coding example now. Like as you can see here, I have opened my Google Colab here. I will be sharing the file with you later on. So okay, so at first we are going to import our NumPy, as we are going to just using some just the basic things. Okay, now we imported this. Now let's define our activation function here. Define sigmoid of, let's say, x here, then it will be returning us 1 over 1 plus np dot exponential of negative x. Okay, so this will be our sigmoid function. Now we're going to create input data, or the AND gate truth table. Let's do this and this and this. At first our 0 0, and then our comes the 0 1, and then comes our 1 0, and finally comes our 1 1. Okay, now if we run this, yeah, now let's create our output labels. Np dot array. Okay, for np dot array we will be having, as we know, the it will be what, it will have a 0, and then 1, then it will have a 0 0, then another 0, and finally another 1. Yeah, that was it. Okay, so yeah, it worked. Now we initialize the weights and bias randomly. Np dot random dot seed of, let's say, 1, and then we declare our weights here, np dot random dot seed of now we are going to use the random dot rand from s2 to 1, and then we will be using our bias np dot random dot rand of 1. Yeah, this was it. And then we are adjusting our learning rate as 0.1. You can modify as per yourself. Now let's write our training loop. Let's say for yeah, okay, for epoch in range of let's say 10,000. Epoch in 10,000. What are we going to do is, at first we will be doing the forward pass. The z will be equal np dot the x and the weights, and we will be adding our bias here, and then we are going to predict, or the prediction, declaring the prediction here, and then sigmoid of our z. Okay, so now we found, let's check our error. To check our error, we will be doing the pred minus z, not z, the y. We declared our y, if you remember. Now we do the back propagation to update weights and bias. Now if we do the back propagation here, weights will be negative equal learning rate multiplied with our np dot multiplication of xt and error, and then we need to do for same for our bias, negative equal learning rate multiplied with np dot sum of error. Now we do our final prediction here. Now let's print us like the final pred, and now we print the sigmoid of np dot of our x comma weights plus additional bias. Okay, let us run this. Okay, so list has this doing this. It should be our transpose for epoch. Okay, just okay, so I found the error here, as like we didn't define this thing as np.array. I was facing this issue here. Okay, I hope now this won't be issue. Let me just cover this and this. Yeah, let's see. Okay, this one. Yeah, as you can see, our final pred here. Okay, so this was it. Now like what are we going to do is what we learned today, the core concepts we mastered, like neuron is just weighted sum or plus some activation functions. We learned about the neural networks are layers of neurons connected together. Then we have seen the forward propagation is a matrix multiplication through layers. Then we seen the even simple networks can learn complex patterns. Okay, now coming next week we will be facing like how does the network actually learns, or the backpropagation one, and then we will be derive the math behind the gradient descent, and we will build a multi-layer network that learns XOR, and we will be implementing a backpropagation from scratch. And like I have some teaser questions for you, like why can't our single neuron learn XOR? You can check that and type in the comment right below. And how do we efficiently compute gradients through multiple layers? Okay, so I have some homework and practice problems for you. Like the questions will be available on the description as well. And for you, the begin for if you're a beginner, the question I have three questions for you, like the implementing OR get using the same code structure, then try different activation functions like step function, the 10h function, and the ReLU function, and do the experiment with different learning rates. If you are in an intermediate level, try to implement this with the NAND gate. Try to create a 2 input and 1 output network with random weights, and finally visualize different activation functions. And if you are in advanced level, try to solve XOR with a single neuron, or if I give a spoiler, it is a type of impossible. And secondly, create a simple two-layer network manually, and finally research why XOR needs multiple layers. You can do your research, you can share your Cola files with me, and you can do like explore everything. Now I have two questions for all of you. Like, why do you think the step function isn't used in modern network? And like, how might the biological brain inspire other aspects of AI? So remember, this is week 1 of a 4-week journey. Keep it accessible but rigorous. The goal is to build intuition and practical skills that will support more advanced concepts in later weeks. Thank you everyone. See you in the next week.